Okay, so I think we should start. So this is the second unusual week in the sense that I am speaking in front of you for 3 hours. But next week we will have one lesson and then a speaker from outside. Okay, so the seminar today will be devoted to connecting spatial infinity with null infinity, and that leads in particular to a new understanding of the so-called Strominger's matching conditions, which I will also explain along the way. Okay, so what is the problem? If we look at the boundary form of the metric, and I recalled it during the first lesson, the previous lesson, well, we assume the behavior at infinity, so the behavior of the functions v, beta, HAB, UA for very large R, well, we are assuming that they have some smooth expansion in inverse powers of R. And this is taken for granted. And a similar expansion is also taken for granted at past null infinity. So if instead of using a retarded null coordinate, we use an advanced null coordinate, v, we would have a similar expansion because the general reasoning leading to the boundary form of the metric and based on a family of null hypersurfaces will also work. And then we will get this expression for the metric with different functions. But again, this expansion is assumed to hold and without really questioning it. Now, also, well, we can see that we have some functions appearing here, for instance, m in V, some other function in V prime. We might ask the question, how are these functions connected? Now, of course, they should be connected where they can be connected. So this is future null infinity, this is past null infinity, and the two connect as we go to spatial infinity. So we can ask, for instance, the question, how does the limiting value as u goes to minus infinity, so I go to the past limit of future null infinity, how is it related to the limiting value of this function, assuming it has a limiting value, as v goes to plus infinity, so to the future of past null infinity. Now, usually such conditions are imposed. Actually, they also involve an antipodal map, but this is somehow related as you go in polar coordinates. We have seen that if I look at a straight line that goes through the origin in polar coordinates, as you go through the origin, the angles are antipodally matched. Okay, but so people have assumed such conditions. They are called. This is one example of a matching condition between the metric on future null infinity and the metric at past null infinity. You might ask the question, how can we justify, or do we have to assume, or can we justify these conditions? And this is an important condition, well, for defining the S matrix, although I won't talk about the S matrix here. That was one motivation by Strominger. And you might ask the question, suppose I give you initial data on a Cauchy hypersurface, I integrate these Cauchy data, I will get some metric, well, first of all, will I get a smooth null infinity with a metric that has the expression I have written in the future, similarly in the past, and will the functions appearing in these boundary expressions fulfill these matching conditions? That would be a way to derive the matching condition from initial data.
Actually, may I interrupt you?
Yes?
So, because in principle, we naively would say that we don't have freedom to impose, since you solve the problem with the Cauchy data, you get something, and either it works or it doesn't.
That's right. That's my point of view. So it's either it works or it doesn't work, and hopefully it works. But you should be able to derive it, to prove it from initial data. So that's the philosophy, indeed. And we will see that things work, but some things don't work. Now, of course, reasonable, well, you have to make some work about what you have to define what you mean reasonable initial data approaching Minkowski at infinity. I will talk about that actually in my other lectures, because, okay, that's the question. So I take initial data on a Cauchy hypersurface. Do they develop into a space-time metric that obeys these conditions? Now, in this seminar today, I will address that question in a simpler context. Indeed, we can ask a similar question, well, in the simpler context of the electromagnetic field. Well, I will even take a simpler context on the next slide. But so on the electromagnetic field, you can look at the behavior, you can investigate the electromagnetic field near null infinity, future null infinity, past null infinity. And usually people assume that the electromagnetic field, so this is the electric component, and the temporal radial component of the electric field, of the electromagnetic field. So that would correspond to the electric field. So it is assumed that it behaves like that at infinity in most work on electromagnetic radiation, and a similar expansion is assumed to hold near past null infinity. And again, there are some matching conditions which have been imposed, for instance, by Strominger, stating that this function and these functions are not independent, but they connect as you go to the past of future null infinity, and here you go to the future of past null infinity. This should be a V. With this antipodal match, well, I will so recall that these are the angles, and the minus sign represents the antipodal map. So in terms of theta and phi, it's not that you take minus theta minus phi, but this symbolically denotes the coordinates of the antipodally related point. So phi would go into phi plus pi, and theta would go into pi minus theta. Okay? So this is usually assumed, and again, in principle, this is something that we should be able to prove from initial data. Now, clearly, to derive that from the initial data, one needs to understand better what happens at spatial infinity. So let me recall the Penrose diagram of Minkowski space. So we are assuming some behavior of the electromagnetic field here. We are assuming some behavior of the electromagnetic field here. This is past null infinity, future null infinity. And we would like to see how the two things connect. So clearly we have to understand better spatial infinity. Also, we would like to know whether the behavior assumed here can follow from a reasonable behavior on a Cauchy hypersurface, like the one here drawn in red. Okay, now actually it's even simpler to ask a similar question, which can indeed be asked in the context of a scalar field. So usually, if you look at analysis of the massless scalar field at null infinity, people will postulate some expansion in inverse power of r of the scalar field as you go to null infinity with some coefficients which are functions of u and x. Okay? And again, we can ask the question, if I give you initial data for a scalar field on a Cauchy hypersurface and integrate the scalar field equation, will I get a scalar field that indeed behaves like that? And also, well, I would have a similar development at past null infinity. This is future null infinity. Can I connect the coefficients in the exponential, at least in the limit when this u goes to minus infinity and v goes to plus infinity? So I can also ask the analog of matching conditions. Now, in this seminar, I will focus exclusively on the scalar field because the equations of motion are simpler. Also, there is no issue of gauge invariance to worry about. But that will really be that will illustrate all the main idea necessary to tackle the problem of matching conditions in the most complicated cases of electromagnetism and gravity. Now, the equations of motion for a massless scalar field are just the Klein-Gordon equation, so box phi equal to 0. And it's very easy to see, and I will go quickly over that because I might come back if we have time later, but I want to go ahead. But I'm claiming that if you assume that the initial data are of compact support, then you can integrate the equation towards null infinity, and you will find that the scalar field behaves as I wrote for large, as r goes to infinity, towards null infinity, or towards past, so towards future null infinity, or towards past null infinity. So these regularity conditions are assumed, can be proved to hold if you take initial data of compact support and integrate the Klein-Gordon equation. Now, there is actually, it's a nice theorem that follows from the conformal techniques of Minkowski space. It's explicitly proven in the book of World on General Relativity. And for that reason, I will skip the demonstration here, even though, well, there are a few slides where it is developed. So if we have time, I might come back. But the idea is that you go to you make a conformal transformation, you integrate the equations on the conformal completion, and then you observe that it's finite on the boundaries, and then using the conformal factor and how the conformal factor behaves as you go to the boundary, you can control the solution.
You assume smooth and compact support, or compact support on C2 or whatever?
Well, smoothness I will probably usually always assume. So here, smooth and compact support. Because, well, I will need the unique existence and uniqueness theorem of that equation, conformally related equation on the Einstein universe, and I guess probably you need some smoothness of the initial data to prove existence and uniqueness. Okay, but
I'm not complaining, just to know.
No, but that I'm also not. I would play it safe and say yes. Okay. Okay, so this is the proof, but I will skip it because we are really interested. Okay, you see, we are interested in long-range fields. And so we would like to be able to deal with initial conditions which are not on compact support. For instance, when we will have to deal with the electromagnetic field or with gravity, we don't want these. We know that these might have 1 over r or 1 over r squared behavior at infinity, but they are not of compact support. So I would like to be able to deal with this more complicated situation. And since this is not treated when you consider compact support, let me not go over the proof here. And so, for instance, just like for the electromagnetic potential, we allow a 1 over r behavior, or for the metric, we will allow a 1 over r deviation from Minkowski space. I will consider a scalar field which, at large values of r, so I'm considering now the scalar field on some t equal constant slice. So I'm in Minkowski space, so Cauchy hypersurface. T x0 equal to 0, for instance, and I'm assuming that behavior, and I allow a 1 over r decay. Then, of course, there will be 1 over r squared, etc. And I want to integrate the equations of motion with for such initial conditions. Okay, so I will use systematically polar coordinates, but I already introduced polar coordinates. I denote the metric on the unit round sphere gamma bar AB here. It was denoted gamma AB on the blackboard, but it's the same thing. So this is just d theta squared plus sine squared theta d phi squared in spherical coordinates. And, well, this is what I said. And the coefficients here are allowed to be, well, they will depend on the angle. Now, if you fix time, of course, that's all they depend on, but I will follow the evolution of these coefficients, so they will also depend on time. But the r dependence is the one explicitly written. There is no r dependence in these coefficients. Okay, so this is what I have, and I want to integrate the Klein-Gordon equation, so very simple equation, linear equation, and ask the question, what is the behavior at null infinity? And null infinity here, since I have Minkowski space, it's really the Penrose diagram. I mean, the null infinity obtained through the Penrose compactification. That's, the metric is fixed. We have fixed metric coefficient in the Klein-Gordon equation. And so I want to integrate the equation. Now, in order to integrate the equation, I will go to hyperbolic coordinates. And I go to hyperbolic coordinates for two reasons. We will see that the equations nicely separate order by order in hyperbolic coordinates, so technically it's very useful. But also hyperbolic coordinates do not have the problems that I mentioned for the Penrose compactification of Minkowski space, that I0 was a single point, so spatial infinity was mapped on a single point in the conformal compactification. But here a lot of things happen at spatial infinity, especially the matching conditions take place near spatial infinity. And the hyperbolic coordinates I will introduce give a nice description of spatial infinity. They resolve spatial infinity, which is not anymore a point. Okay, but let's see how they are. Let's be concrete. So I will introduce new coordinates instead of t. So the angles I don't touch. So everything, I will write formulas in the two-dimensional TR plane. And I will introduce these coordinates, new coordinates which I call eta and s, which are defined as follows, which of course assume that I'm in the region where r is greater than the absolute value of t. Now this is the inverse transformation, I mean this is just algebra. And let's write the metric in these new coordinates. And in these new coordinates, here is the metric where eta HAB dxa dxb is the metric on the hyperboloid. You can see that eta equal to constant is an hyperboloid. Minus t squared plus r squared is equal to constant. So you are foliating Minkowski space by hyperboloid, okay, for different values of eta, and just make the coordinate transformation. This is just a direct algebraic computation. Just substitute in the Minkowski metric using t and r given here, and this is what you get. Okay, and as I said, this is in unusual coordinates, but useful coordinates, the metric in this coordinate system. Now you should say that you should see that when s is equal to 1, that means that t is equal to r. This defines light rays. And we see appearing some singularity in the expression of the metric in that limit. So something will happen at s equal to 1. That actually is the connection between spatial infinity, as we will see, and null infinity. But so let's recall that. Keep that in mind. Okay, but so this is, in terms of the Penrose diagram of Minkowski space, the region which is being covered by the hyperbolic coordinates. We need r greater in absolute values than t, so this is r equal t, r equal minus t, and we are just in that reddish pink region. Okay, so this is the region I will be looking at, but it's nice because it contains, for instance, this Cauchy surface, t equal to 0, and it contains also spatial infinity and the region where the two null infinities meet. Okay, so for my purposes, this is a good region. And as I said, it has a nice feature of resolving spatial infinity in the sense that as you go to infinity along space-like radial direction, in the case of the Penrose compactification, I told you all space-like all Cauchy hypersurface will end at I0. So they will be lined like this, like this, like this, like this, space-like, but they are always ending in I0. So they give, we have a very poor description of I0, of spatial infinity in the conformal Penrose coordinate. Now the hyperbolic coordinates are not conformal, so causality might be more subtle to analyze directly. I mean, we cannot, but it has a nice feature of resolving spatial infinity. Let's see that. So if I go to infinity along a space-like radial straight line, so smaller than 1, so that indeed this is space-like. Now recall that in the case of the Penrose compactification, we would always end at the same point at infinity. But here you see that, well, of course, you take the limit r goes to infinity, which is the same as eta goes to infinity in that case, to reach the limit. But you can see that S, which is the quotient, the ratio of t over r, will go to a value that depends on the spatial radial line. So contrary to what happened in the Penrose coordinates and Penrose compactification, where no matter what A was, you would always end up at the same point, which was called I0. Here, depending on the value of A, you will end up with a different value of S. So infinity will be eta equal infinity, so that's still something we will have to handle. But there will be different value of A, which gives information on where you land, I mean, the direction at which you land to infinity. Okay, so from that point of view, they are good. They resolve spatial infinity. They will have a bad feature, which I will mention later, but for the moment, this is good. And so recall also that null infinity is obtained when t is equal to r plus b. So in the limit, you can forget about the b. And so this would correspond to s equal -1 for the past, s equal +1 for the future. Okay. This is actually what I said. So if you go from a value of s which is in between and then go to s equal to 1, you are reaching the path of future null infinity, and vice versa for s goes to -1. Okay. Now, as I told you, the idea is really to control the solution of the Klein-Gordon equation and see how it behaves as we go to null infinity. So we write the equations in hyperbolic coordinates. Now, this is the expression of the D'Alembert in arbitrary coordinates. Well, I will set it equal to 0. The D'Alembert is really 1 over square root of minus g times that. But since I'm setting that equal to 0, this is the Klein-Gordon equation. I didn't try the 1 over square root of minus g. So here it is. And then you just compute, we have the metric. It's easy to write the inverse component of the metric. The metric is diagonal. So if you plug in the value of the metric into the equation, this is what you get. Okay, you get something that will depend on second derivative with respect to eta, but the metric is not the metric in Minkowskian coordinates, so you get some factors which come in. These are curvilinear coordinates. And I have to tell you what is curly curly d is a covariant derivative with respect to the metric of the on the hyperboloid. Okay, and I'm raising and lowering these indices. So the index A takes the value, well, one value corresponding to S and two values corresponding to the angles. We are on the hyperboloid. Okay, and so this is the D'Alembertian of the hyperboloid, and then there is also a term which contains a derivative with respect to eta. Okay. Now, also I should have mentioned that the slices s equal to constant are not hyperplanes in the case of, but they are cones, because s equal constant is t is equal to some constant time r, and so this is really a cone. But that will correspond to with the hyperplanes when s is equal to 0, because that's just t equal to 0 then. When the constant is not 0, you will have cones, but which are space-like. Okay. Now, because the slice s equal to 0 is one of these Cauchy hypersurface on which I was assuming some expansion of the field in inverse power of r, and since r coincides on s equal to 0 with eta, recall eta is square root of minus t squared plus r squared, so if t equal to 0, eta and r are the same, I will assume the following, I will take the following expansion for eta, for phi, for the scalar field, which will reduce when eta is equal to S is equal to 0, so when this XA, the S which is contained in XA, these are the coordinates on the hyperboloid, is equal to 0, that will reduce to the expansion I was assuming. So that will match the assumption, the expansion I was assuming on the Cauchy hypersurface, but I'm making that also for all value of S, where we'll see whether this is, I'm claiming that this is compatible with the equations of motion, and indeed it is, because if we plug that into the equations of motion, you can show that they decouple order by order in inverse power of eta. And this we can understand from that expression. You see that here, you see that here I'm differentiating twice with respect to eta, but here I have a power of eta cube and eta minus 1. So I have also eta squared in the numerator, but I am differentiating twice with respect to eta. So this will be homogeneous. This is also homogeneous. So when you act with this operator on a fixed inverse power of eta, you will get something which is also a fixed power of eta. There is no mixing between the different terms in the expansion. And this is a very good feature of hyperbolic coordinate, because then I will be able to integrate the equations for the coefficients order by order and eta. Okay, so that's why people like hyperbolic coordinates. And what do you get? Well, you will get the D'Alembert here on the hyperboloid plus some factor times phi, factors that will depend on k, because you will take differentiation with respect to k. And so if you do the computation, here is what you get. Not too complicated. You get that the D'Alembert of phi k, which is a function on the hyperboloid, plus k squared minus 1 phi k is equal to 0. So you see there is complete decoupling. And that's why we will be able to integrate the equations and to investigate their behavior as we go to null infinity. So now if you expand using the metric on the hyperboloid, so I expand that operator, okay, and there will be a part that comes from S and a part that comes from the angle. You expand. It's again a direct algebraic derivation. Here is what you get. So you get second derivative of S, which are in the D'Alembert, but then you get also the Laplacian on the two sphere. Okay, so that comes from here, and well, actually there is a factor of 1 minus S squared. If you look at the metric, there was some factor of 1 minus S squared coming in front. And so if you do the computation, here is what you get. Okay, so again, this is straightforward algebra. I don't think it's very instructive to repeat it. You can trust me. It's also in published papers. So here is what the equation becomes. So we see that we get independent equation for each order in the expansion, phi k, and the equation for phi k, well, depends on k and takes the following form, which is, and that's of course not a surprise because the Klein-Gordon equation is linear. It's a linear equation in, it's a partial differential equation, but which is linear in phi, okay? But that Klein-Gordon was linear, so it's not a surprise. Okay, so this is what I said, and now we would like to integrate these equations, and one can integrate for all orders, and that's in the literature, but to convey the message, it will be sufficient to look at the first two orders, at phi 0 and phi 1. Now, phi 0, remember that there is a shift in the notation. So phi 0 is a coefficient, it's a leading coefficient, sorry, it's here. Phi 0 is a leading coefficient in 1 over eta, or 1 over r, when s equal to 0. So you get phi 0 over eta, plus phi 1 over eta squared, plus phi 2 over eta cubed. So there is a shift in the power here. So k here is the coefficient of eta minus k minus 1, okay? So I will look at the equation for phi 0, the leading term, and then to give an idea of what happens with the subsequent terms. So the leading term is in a sense the most interesting one, but then the subsequent terms are also, it's nice to know how they behave, but once you have understood the first subleading term, you really understand how it goes for all the others. So I will only investigate the equation for phi 0 and phi 1 for this reason. Okay. Now, well, actually for all of them, because we have the sphere, we can develop, we have function on the sphere, we can develop the unknown function phi in spherical harmonics. So I will expand in spherical harmonics, and I will call the coefficient theta. And of course, theta will, for each values of L and M, so M is smaller in absolute value than L. L takes value 0, 1, 2, 3, etc. So all the harmonics. So this would be the corresponding coefficient, which is a function of S that we have to determine. Now, I have included the factor here to simplify. So why? It's not terribly deep. It's to simplify the differential equations that will the coefficients here obey, that I have included this. We will see that immediately for phi 0. It's by including this coefficient that I get a very familiar equation for the coefficient, which is the Legendre equation. Otherwise, I would have to rescale the functions to get the Legendre equation. But so, apart from that, there is really nothing deep here. It's just to get equations that have been treated in the literature in the form they have been treated in the literature. Okay? But it's an important factor because we know that S equals 1 or minus 1 corresponds to null infinity. So indeed, that's a factor which will have its importance when we discuss the behavior as we go to null infinity. But so now you rewrite the equation for phi k in terms of the coefficients of the spherical harmonics. Well, and the spherical harmonics are eigenfunctions of the Laplacian on the sphere with a function eigenfunction, the eigenvalue is minus L plus 1, as we know. And so this is what you get. Okay, I've expanded and I've taken into account the rescaling. Once you have done that, here is what you get, the equation for the coefficient theta k. And as I said, I will study the behavior of these solutions for the first two values of k equals 0, which controls the 1 over r component in phi, and k equals 1, which controls the 1 over r squared term in the expansion of phi. Okay. Now, as I said, if you are interested in all values of k, this is given in the literature in that paper. Okay, so let's go with k equal to 0. So that controls the 1 over eta term. And here is what the equation reduces to. So let's see what happens. If k is equal to 0, you get minus 2 here as coefficient. This is absent. And this then reduces to the following equation, which you might remember is just the Legendre differential equation. So that's the reason why I had included this factor. Okay, now the Legendre differential equation is an equation that we have been exposed to very early on in our career. So, well, maybe we forgot the results, but that is well documented in the literature. So there are two types of solution. Well, this is a second order differential equation, so you would have two independent solutions. Okay, I will call one of them P and the other Q. Now, for the value 1/2, you can forget that in this talk what is its meaning. It's related to the choice we made of k equal to 0. So, but instead of writing 0, I've written 1/2 because there is another parameterization which is useful. But so now we also see that this solution depends only on L. Well, that's because we have spherical symmetry, so M is irrelevant in that equation. We have only L which appears. So that's why I'm calling the solution only with L, no M. And there will be two independent solutions. One is P, which I call P, and one I call Q. And so the general solution will be a linear combination. It's a linear equation linear combination of these independent solutions. And for each set of L, I will have two independent solutions. Now, one of these independent solutions are just the Legendre polynomials. Okay, the Legendre polynomials are solution of the Legendre differential equation. And they are polynomials, so they have a very nice and smooth behavior in S. Well, note that this equation is a differential equation, but they are singular points. S equal 1, S equal minus 1. Yeah, well, if you divide by if you put it in canonical form, and you will find that indeed you have to divide by 1 minus S squared. So there are two singularities, S equal 1, S equal minus 1, but these are Fuchsian singularities, so these are well under control singularities. Now, one of the two solutions happen to be a polynomial, that's nice, and is completely regular at the singularity S equal 1 and S equal to minus 1. But the other independent solution is not a polynomial. It's called, well, it has a name because it has been studied. They're called the Legendre functions of the second kind, and I denoted them by Q. And these are singular. They have logarithmic singularities, in fact, as I will explain in a second. So, which is not surprising. I mean, we have singularities in the differential equation, so we can have singularities at the same points in the solution. So there is one regular solution, Legendre polynomial, and one which has logarithmic singularities, which is the Legendre function of the second kind. Okay, let's be a little bit more explicit. Okay, I'm just rewriting the general solution. Here it is. I have plugged in what I wrote on the previous transparency. And now we want to understand what happens when we go to null infinity. And I told you null infinity is S goes to plus or minus 1. So what happens when S goes to plus or minus 1? Well, this seems to be fine, but we have singularities here. This is a polynomial, so a polynomial in S, when you put S equal to 1, it's smooth, but this contains logarithmic singularities. So let me be more precise. Again, if you go to the literature, so I'm not rederiving that here, this is again something which is well known, you can show that you can express, there is a recurrence relation which expresses the Legendre function of the second kind for any values of L in terms of the one for L equals 0 and polynomials. So this would actually be the Legendre polynomial, so you would have this times the Legendre polynomial, then plus another polynomial of degree L minus 1. So this is what you get when you solve the recurrence relation. I mean, these solutions to these equations, which are classic equations, have been much studied in the literature. In particular, it's known that there are all sorts of recurrence relation, and one of them gives you QL in terms of QL minus 1 and QL minus 2, and you can solve that, and this is what you get. But this is interesting because it shows that the singularities in QL are actually the singularities in Q0. Because this is a polynomial and this is a polynomial. So when S goes to 1, this just takes some finite value. Okay? So we need to know better the singular behavior of the Legendre function of the second kind Q0. And again, this has been very well studied in the literature, and people know that actually this function is given by that expression. You can check that it fulfills, it's a solution, independent solution of the Legendre equation. And you can see that it has singularities when S is equal to 1 and when S is equal to minus 1. So the argument of the logarithm is either 0 or infinity. So that goes indeed, that diverges logarithmically. Okay? So if we want to study the behavior of phi as we go to null infinity, we have to pay attention to that term, essentially. Well, actually, and this will be also useful. Will be useful for what I will say later. It is also known that the Legendre polynomial has some definite parity that depends on L. Well, actually, when L is equal to 0, the Legendre polynomial is a constant. When L is equal to 1, the Legendre polynomial is S times a factor, which depends on normalization conventions. And so the parity properties of the Legendre polynomial are that they are even when L is even, and they are odd when you change S into minus S when L is odd. Now, this is an interesting transformation because we know that in our description using hyperbolic coordinates, S equal 1 is past of future null infinity, S equal minus 1 is the future of past null infinity. So relating minus S to S in the limit when S goes to 1 is going to relate the limiting, the past of future null infinity with the future of past null infinity, which are precisely what people do when they investigate matching conditions. So matching conditions typically will have to compare S equal to 1 with S equal to minus 1. So it's nice to know how the polynomial behaves under this transformation. Now, the Legendre function of the second kind have the opposite parity property. So if L is even, they are odd, and if L is odd, they are even. Okay, now if you combine that with this, recall that they come with spherical harmonics. Spherical harmonics have also definite parity properties. When L is even, they are even. When L is odd, they are odd. Okay? Now, if you can then consider the product of PL with the spherical harmonics, which is what occurs in the solution. You see, we have PL times the spherical harmonic, so S here, spherical harmonics. We have Q times the spherical harmonics. These two terms will have opposite parities under the antipodal map, where I simultaneously change S into minus S, and I do the antipodal map on the sphere. This term, the P term, will be even. It will be either a product of even with even or odd with odd, while the Q term will be odd. It will be a product of either odd with even or even with odd, but because they have different parities, there is always a minus sign, independently of L. Okay? So these two terms, these two different pieces in the general solution of the for phi 0, the P term is even, the Q term is odd, under the simultaneous, under the, what I will call the antipodal map on the hyperboloid. So you are simultaneously changing the sign of S, so you are exchanging future with past, and you are also making the antipodal map on the sphere. Okay. This is, I will call the P branch the sum of the P terms, and the Q branch the sum of the Q terms. Okay, now it turns out that if we want to go to null infinity, hyperbolic coordinates are not completely good. They need to be improved, and let me explain you why. I0 has been resolved in hyperbolic coordinates. This is nice. But if you look at the description itself of scri plus and scri minus in hyperbolic coordinates, it turns out that you cannot distinguish the various points of scri plus and scri minus. So for instance, let's consider scri plus. And let's go to null infinity along a radial null geodesic, so T equal R plus B. And so I will go to large value of R, so I'm going to infinity. You can show that S, which is the ratio T over R, as R goes to infinity, will always go to S equal 1, and eta will also always go to eta goes to infinity. So all points along scri plus will have the same coordinates s equal 1, eta equal to infinity, no matter where the null geodesic lands on Scri+. So from that point of view, these hyperbolic coordinates have a good feature in what concerns I0, but in what concerns Scri+, they are not so good. Now, we would like to have coordinates since we want to describe the passage from I0, from spatial infinity to Scri+. We would like to have good coordinates which simultaneously cover well at least a portion of Scri+ and spatial infinity. And these are, okay, this is just what I said. So you are compressing Scri+ into a single point, in a sense. And so this is not good. And so we need new coordinates, and Friedrich has introduced these new coordinates which are very good to describe the portion of Scri+ which is close to I0, if I can say so, and I0 which is also resolved. So let me give you the coordinates and then comment. And actually these coordinates will be used in the seminar by Valiente Krohn next week. So let me describe them here. So I will not change S because S was very good in describing the various points on the hyperboloid and direction. So S I keep as it is. But rho, I will change, sorry, eta, I will change into a new coordinate rho. Now the metric in these coordinates is kind of ugly because it's not even diagonal, but we will see that it describes, it fulfills the purposes that we want it to fulfill. So, well, first of all, it's clear that it's conformal to this metric. And since causality is invariant under multiplication by a conformal factor, I might as well consider this metric to understand the connection between the causal connection between the various boundaries. And it's clear also that spatial infinity will still be blown. So when eta goes to infinity, rho with fixed s, rho will go to infinity, but the value of s will be between -1 and +1. So you still have spatial infinity being blown up. I mean, it's not a single point I0, so we keep that good feature of the hyperbolic coordinates. But if you look at null infinity, so it's still, okay, then I should also say that rho goes to infinity. It's infinitely far away because I would have to integrate d rho over rho. I will get a logarithm of rho. So infinity still in these coordinates is far away. But if you look at the metric induced on rho equal to constant, so if rho is a constant, this term is absent, d rho, this term is absent, you see that it is a metric which does not depend on rho. So the metric induced on rho equal constant, in particular, if you take rho goes to infinity, is just this metric, minus ds squared plus d omega squared, which is the metric on the unit cylinder. So spatial infinity is represented by a cylinder which is infinitely far away in the coordinate rho, well, and also in terms of this metric, but which has a metric which is finite and given by minus ds squared plus d omega squared, which is a canonical metric on the cylinder. So this is actually, it was on this transparency. This is what I said. Now, if you go to Friedrich, actually he was not using rho, but he was using 1 over rho. So that brings infinity to the value 1 over rho equal to 0. But this is, in a sense, a technical detail. So in one case, the physical space will be inside infinity, rho equal to infinity. In the other case, it will be for greater value of chi. But that's, I will draw actually a picture because that's probably going to be drawn next week. You see, well, maybe I go back to here. No, I will first describe where is null infinity. So as you go to Scri+, well, S was related to the quotient T over R, so that always goes to 1, okay, as you go to null infinity. But the new coordinate row, because we have inserted, let me show this factor. Because we have inserted this factor, when you go to infinity along null directions, rho is not going to the same value. It goes to a value that depends on the particular geodesics you are considering. And so you have this feature that I described, that scry minus in hyperbolic coordinates was reduced to a point. Actually, now we are also resolving that, and we do have a good representation also of scry minus. We have different values of rho will describe different points on scry minus. In the other case, eta was always going to infinity no matter what, and so you could not tell the difference. And so null infinity in that representation, but it's not a conformal representation, is given by S equal 1, so it will be a horizontal surface. And so the picture we have is the following. I'm looking for a chalk, okay. So you have the cylinder at infinity, and then you have the slide, and this is scry plus, S equal 1, and this is scry minus, so S equal minus 1. They are surfaces, I mean, they are parameterized by rho, different values of rho, and different, well, of course, the angles I'm not writing, so you have a cylinder like this, and of course, each point here is a sphere, and then we see that this part of the cylinder, so for S strictly smaller than 1, strictly greater than minus 1, is spatial infinity. So spatial infinity has been blown to this, okay, and null infinity is here. And this boundary is the critical place where null infinity meets spatial infinity. And here, past null infinity meets. So they are sometimes called the critical sets. And these are actually, we want to understand how things behave. And actually, the matching conditions are conditions relating this, the value of the fields here, with the values of the fields here. Okay. Now, in the original Friedrich coordinate row, well, spatial infinity is somehow inside. So the picture you have is that you have a cylinder, but it's the outside of the cylinder, which is so you have a surface. I don't know how to draw. So there is a hole. Okay. So it's the outside here that is interesting. Okay. Yeah, I should. So this would be scry plus, and you have to go here, okay? This is spatial infinity. So you have a cylinder, and it's null infinity is here, past null infinity is here, and the points of the manifold, the point of space-time are all the points outside of the cylinder and between these two values. Here, all the points are inside, okay? And this is really at an infinite distance, so I mean I should put some. Okay, so this is the picture, and we want to. But what is nice is that the metric which is induced here, after the conformal rescaling, is just the standard metric on the cylinder, and the metric which is induced here is just, well, you have lost track of the null direction, so it's just d omega squared. Okay. But so, well, we are covering the same region, but this is again on the Penrose diagram. But of course, on the Penrose diagram, well, we have learned that I0 is now really the cylinder. The critical sets, or the limiting sets as you go to I0 here and here, are just the top and the bottom of the cylinders. Okay. I mean the intersection, sorry, of the top, so they are just the circles here. Then all of null infinity is here. Similarly here, well, and it's infinite, so it's, well, there is, I plus would be some kind of point which is removed from here. Then, what do I want to say? Yeah, and then S equal, this is, you see, scribe plus is S equal 1, but rho can take any finite value. Okay, and rho equal to infinity correspond to the limit as you go to I0, because I0 has a value rho equal to infinity in my parametrization. Okay, so now we have all the tools to understand the behavior of the fields. This is again what I'm just repeating what in writing what I said. So the behavior at the critical surfaces is really key for understanding the matching conditions. Okay, and you will hear more about these critical surfaces and behavior of the field near the critical surfaces next week in the seminar by Valiente Krohn. Okay, and then also, but it's rather obvious. Of course, if you first make S equal to 1, you arrive at null infinity, and then rho goes to infinity, you go to the boundary, to the critical sets. But then you can also do the opposite, go to spatial infinity, and then take the limit as you go to null infinity. Okay. Okay, this is just rather obvious, so maybe I leave you a little time to read. But essentially, this is what I said. Repeat it in writing. Okay, so we have these good coordinates to understand the behavior of the fields. And now let's go back to our solutions, phi 0, and see in these coordinates how it behaves. So now I just do the expansion, and here is what I get. I get some, you see I had a factor, a square root of minus s squared that was floating around, but I have 1 over eta. When I express eta in terms of rho, I get another square root of 1 minus s squared. That's why there is no fractional power anymore here. And we would like to understand the behavior of this expression as s go to 1 and s goes to minus 1. But let's focus on future null infinity. S goes to 1. Now, of course, this is good because this vanishes. But remember, there are terms here which, well, the polynomial is nicely behaved, but there were some divergences here. So the first question is to see whether the diverging factor here is cancelled by the 0 coming from here. And the answer is yes, because, as I said, p is bounded, so when you take that limit, it doesn't matter. But this diverges only logarithmically. So I have, for instance, logarithm of 1 minus s, but it's multiplied by a factor of 1 minus s. So the logarithm doesn't blow up sufficiently fast, and so we get 0. So the first observation, but that's not very interesting, is that phi goes to 0. But after all, if we knew that phi was going to 0 anyway, to infinity. So, okay, phi goes to 0 at infinity. That's good, but we would like to be more precise. Now, in order to be more precise, I will go, because actually I want to compare with these boundary coordinates and the expansion in boundary coordinates. I will, in that expression, which I know is in good coordinates near null infinity, and so I can use that expression and now substitute. I will substitute, express s and rho in terms of the standard null coordinates u and r to see what happens. Now, again, it's a straightforward exercise of changing variables. Okay, so I think you can trust me, but so you are just substituting. You have to trace. I mean, we have s. S was defined in terms of t and r, well, actually that's the easy part in terms of t and r, and t is u plus r, so that's indeed not a big surprise. You need a little bit more exercise to check that rho will be given by that expression. And then 1 minus s squared, well, you just, well, when you take s squared, this one will go away. So we will get the double product. And then, well, actually, I could have written things explicitly, but that will be, you would get u squared over r squared, minus u squared over r squared. But I just need to know its order r minus 2. OK. And then I put that in this expression and recall the limit that is of interest to us is u goes to minus infinity, just to see the behavior at the critical surfaces for the matching conditions. But more generally, any value of u is of interest because I'm interested in not just at the behavior at the critical surface, but everywhere at null infinity. So let me just substitute. Now, here, OK, maybe I can give you a few words. So this, well, 1 minus s squared, we see that it gives me, to leading order, something that goes as 1 over r, okay, with a factor of minus 2u. But to leading order, so let's just look at the leading order, rho will give me a factor of 1 minus 2u, so the u will cancel to the leading order 1 over r. Okay, but then the rest, so that will give me the control of this term and this term, but then the rest here I need to control. Now, as s goes to 1, because I'm at null infinity, this goes to some constant, okay? But this is more tricky, as we know. So let me just do the expansion. And so I have, so this is just what I said, the factor of 1 over r coming from rho and 1 minus s squared. But then I have here, I have expanded QL using the expression for the Legendre function of the second times in terms of, I express that in terms of Q0. And I have Q0 of S, and S is 1 plus U over R. Now, as I told, and then it's multiplied by polynomials, so we take some constant value at S equal 1. So I just substitute that. So the tricky piece is this one, okay? Now this one is just, as I said, the logarithm. So I have to expand this logarithm. So I'm just substituting 1 plus u over r in that expression. And so clearly you will get log r, then some log of, there was a 2 somewhere, and log of minus u. So I will, why do I? Yeah, I'm just substituting that in here. Huh? So I have 1 plus, I have to replace by 1 plus u over s is equal to 1 plus u over r. So I have to substitute. So if you do the substitution, you will get a log r term and a log minus u term, which is what I have written here. Okay? So there is a logarithm over r. So if you plug that into this expression, you see that the Q branch will develop a term which is log r over r. So it's true that it goes to 0 when r goes to infinity, when I go to null infinity, but it doesn't go to 0 as fast as 1 over r. It dominates 1 over r. There is a log r over r term. Okay? And that's just because this Q branch, I mean this Legendre function of the second kind develop logarithmic terms. Okay? Now, of course, you get something which, as you take the limit, u goes to minus infinity, will get some extra divergence, but which is paired with this one. They go together because they came from S. Okay, but the moral of this computation is that the leading term in the expansion near infinity for generic initial conditions will not start with 1 over r, but will start with log r over r. That will be the leading term, unless the Q branch is absent. Now, usually people assume that there is no log r over r term. which means that they are usually assumed that the Q branch is absent in the leading term. So they impose the condition that the coefficient of the Q branch are all 0. So recall, we want this, we would have this a contribution to log R over R from all these terms. So I will have to assume that the coefficients are 0 for all values of L, which means that I will only be left with the P branch, which behave much more nicely. I have 1 over R, it starts at 1 over R, and then there might be 1 over R squared term, but that's it, okay, coming from here. But it does start as 1 over R, no log R over R, and actually there will be no log R at any time. Okay, but so we will assume, we will impose to avoid log R over R that the Q branch is absent, so phi will reduce to this, to leading order, but well, this is what comes from phi 0. Huh? And so it will obey this, this condition. We have seen that this product had the property for all L that it was even under the antipodal map accompanied by the exchange with past infinity with future infinity. Okay? Now I should say also, if you have this property, it's clear that the derivative with respect to S will have the opposite, well, this will be useful for the sequel. But so what we have learned is that if we want to eliminate the log R over R term at infinity, we must assume that we have only the P branch, which means that we are at S equal to 0. So what does this tell me? At S equal to 0, phi should be even under the antipodal map, and the S reduced to time at S equal to 0, and the time derivative of phi should be odd under the antipodal map. Now we'll see that this is phi, and this will be the conjugate momentum to phi. So we will see that the conjugate momentum to phi will have to be odd to leading order, and the field will have to be even. This guarantees the absence of log R over R term in the expansion. Now we can also say something about the matching conditions since we compare minus S with S, that if you look at the leading piece in the asymptotic expansion, well, U will be replaced by, so you take the limit as U goes to minus infinity, so that's S equal 1, and this would be S equal minus 1. So we see that because it's even, we will have these matching conditions. So we can establish matching conditions between the leading orders in the expansion appearing at infinity because of what we had to impose. Okay? Now, this is for the leading order. Now we might ask the question, what about the next orders? Okay? Are there questions about this? But the nice feature of this computation is that you can repeat, at least in principle, it's the same computation for electromagnetism, but also for gravity, as we will see later. So that's why understanding fully the scalar field is very useful for more complicated fields. Okay, so now let's go to the next.
I see that the Q part has to disappear for you to have the right asymptotic you expect from null infinity, but can you argue that you should not question this?
Okay, actually it's a good, I will comment on that at the end. So maybe when I discuss the Hamiltonian formulation, I will have another independent reason for imposing parity conditions, but we could impose the opposite ones, namely only keep Q and drop P from the Hamiltonian point of view. And so, of course, null infinity is in bad shape, but from the Hamiltonian point of view, I don't have an argument to eliminate that. Okay, but so I think indeed we might question that.
So for the moment, what we can somehow take away is that this antipodal match corresponds to choosing to remove the branch, the Q branch.
Yes, exactly. Now, if you keep the Q branch, well, first of all, you have some log R over R singularity, but if you could compare the coefficients at past infinity and null infinity, and you will find that they obey matching condition, but with the opposite sign, which, after all, could be accepted. Okay.
It would be inconsistent with Bondi asymptotics. So
It's inconsistent with Bondi asymptotics because Bondi asymptotics, well, I've written them only for the metric, but you can also consider matter fields and study the behavior of the matter fields close to null infinity. And, well, they have to rescale with a conformal factor according to the conformal weight, but this is well known. So the scalar field will come with some power of omega, the electromagnetic field, no power of omega, etc. And then people have assumed that these fields were smooth at null infinity, the rescale fields. And that would be in contradiction with what I wrote. I mean, that implies that they have a nice expansion in powers of 1 over r that starts as 1 over r. So this would be in conflict for the scalar field with the usual assumption of Bondi and Penrose near null infinity. But if you drop the Q branch, at least to leading order, it's in agreement. It might not have the full so-called peeling property that you have an expansion in 1 over r, but that goes rather fast. I mean, 1 over far, sorry. We will have log at the next order in any case, but they will be subdominant.
those are expected from different people.
They are expected from different people, but they are in contradiction with a strong peeling property of the Weil tensor, which is assumed to have nice expansion in powers of 1 over r up to some point. But I think since they are there is the n-type.
For theoretical reasons, not for physical reasons.
Yeah, but I would even say that for physical reasons, to avoid log r over r is very difficult. I don't know. Well, this is physical in a sense. I don't know what you call mathematical reasons.
Well, for me,
the original reasons.
Is something which is required to have nice Penrose charge, etc., which seems very questionable.
Yeah, I think it is, and this is one way to see that they are questionable. Because let's go quickly over the next order, because okay, the next order again you get this is what you get a nice equation, second order linear with respect to S for the coefficients in the spherical harmonic expansion, and you can construct the general solution. Which actually you can see that when L is equal to 0, it's a very simple equation. It's just d2s theta is equal to 0. So there is a constant piece and there is a piece linear in S. Okay? But then for L greater than 0, actually this you can relate to the so-called equation for Gegenbauer polynomials or ultra-spherical polynomials, which so this equation has been studied in the literature, and again it has one set of solutions which are polynomials and one set of solutions which are functions which are called the associated functions of the second type. The polynomials, being polynomials, are regular at s equal to 1 and s equal to -1. The other associated functions, well, actually s equal plus or minus 1 are indeed singular points, but they are Fuchsian singularities, so there is a control of the solution. Well, and but they would diverge at these singularities. And, well, they diverge more badly than logarithmic. They have the logarithmic terms, but then they have also divergence, which are polynomials in 1 over minus s. So for this one, it's just 1 over 1 minus s. But if we were looking now at the next order in the 1 over r expansion, we would get 1 over 1 minus s squared, so more serious. So the singularity gets more and more dramatic. Okay, so, and this is well documented in the literature. You see, the nice thing is that the differential equations with respect to S is an equation which has been studied in the literature. So once you have appropriately redefined the variables, you just go to the literature and you get the behavior, the solution and the behavior of the solution near the singular points. Okay, so we have polynomial solution, very nice, but then we have also this singular solutions, which appear, so you can again construct recursively from 0 to all values of n, and here is the recurrent. I mean, and the recurrence leads to this solution. So the singularity is here. Well, and there is also a singularity here, which is of the same type. Okay. Now, parity properties of these solutions are also very nice. Well, that's actually because the coefficients of the differential equations have nice parity properties. So if you replace s into minus s, the equation is invariant. So you know that the solution will split into, you can split according to parities, and it turns out that these would be the polynomial solution, and the non-polynomial solution obeys the opposite parity property. But so we repeat the same analysis, and then you plug that into the solution phi, and there is a 1 over eta squared that comes here, and this comes from integrating the differential equation. Okay? But then we go to Friedrich coordinates by making this substitution. Okay, then we get some extra power of s squared here. This is the solution with L strict greater than 0, and this was the polynomial solution corresponding to L equals 0. Yes. Okay, so here is the solution. Now, it doesn't say much, but you have to look at now at the behavior as s goes to 1. So we want to go to null infinity. So we want to make s goes to 1. Now, again, as s goes to 1, where do we have everything is nice and finite except the q's. Okay? But q has a singularity which was in 1 over 1 minus s, and here I have 1 minus s squared. So again, we can say that the solution will go to 0, but of course we knew that it was going to 0. So this is not a big piece of information. What is more interesting is to see how it goes to 0. What are the different terms in the expansion? And because there is a logarithmic term here, you recall there is a logarithmic singularity in this function q. Okay, when you put that in the expansion, you will generate subdominant logarithmic term. So there will be no log r over r term anymore, because, I mean, if you impose this parity condition on the leading coefficient, but there will be a log r over r squared term coming from here. Unless you impose parity condition on this subleading term, but I think there is no reason to impose this parity condition. So I think we have to live with subdominant log r over r squared term, which would correspond in the Bondi form of the metric to logarithmic terms that I have not written, and that you were asking about, but they are of lower order. So they will not spoil the asymptotic analysis of the symmetries. Okay, they don't interfere, and actually we will indirectly be convinced of that because I will be able to do the analysis, asymptotic analysis of the symmetries at spatial infinity on the initial data, and they are there already. So they will still be there when you propagate. Okay, but so they will be subdominant terms. Now you might say, well, this will generate terms which are of order 1 over r. If you look at what comes from here, there will be a 1 over r term. So you might say this might affect the matching, because the 1 over r term is the one which is relevant for the matching condition. But you can show that it will be multiplied by a power of 1 over minus 2u. So when you go to the critical set, where u goes to minus infinity, it's the contribution coming from this subdominant branch will disappear. So the matching conditions are the one that you derive from the leading order. Okay, they are not going to affect the matching condition between the past limit of future null infinity and the future limit of past null infinity, because there is also a u dependence. S, when you express s and rho in terms of u and r, there is some u dependence which appear. We saw that explicitly. I have not written it here. And it turns out that these terms go away in the limit where u goes to infinity, minus infinity. Actually, it's written here, so we can see that actually. So I did the substitution explicitly. So the p branches just go as 1 over r squared. This is what it behaves just as what we expect from here, but the q branch is more subtle because of the singularity at s equal to 1. So this part will contribute this, so 1 over r, but you see that at a generic point of null infinity it will be non-zero, but as u goes to minus infinity it's scaled, so it will not affect the value of the field at the boundary of null infinity. And this term again, if you do the expansion, this is what you get. Okay, there is a 1 over r term that comes, but again it's scaled by this. As u goes to minus infinity, it goes to 0, so at the boundary here, it goes to 0. And so the matching that I wrote, it's unaffected.
Sorry, the log seems to remain, because there is no u.
Yes, the log is remain, but it's subdominant. So the matching was really comparing the coefficient in the 1 over the 1 over r term. Okay, so I'm saying it does contribute to 1 over r term, but as you go to the past limit of along null infinity, it goes away. Okay. But indeed the subdominant term with involving r have singular behavior, but they are subdominant with respect to r. So it always also depends on how you take the limits. So if I first multiply by r and goes to the limit of past null infinity, this will still be a dropout. So this will be the relevant term when I want to do the matching. Now, as we said, if you don't like the subdominant log term, you would need to impose some parity condition to eliminate the q branch, but I don't think we should do that. And I see no good reason, so I believe we have to live with logarithm. And if you have good physical reasons, independent from the discussion here, to keep them. Sorry?
I saw Thibaut Damour add in the physics. Like
okay. I think we have to, they are there, period. I mean, you
do get log in.
And so, of course, it's a bit surprising because there is no log in the initial condition. This is a scalar field. I didn't assume any log on the initial hypersurface, but when I integrate to null infinity, log appears, are generated. Okay, so let me quickly end by going to the Hamiltonian formulation of the scalar field, and this is a way to introduce also what will come in the next lectures, where I will consider the electromagnetic field and gravity. So, and we will get from here an independent reason for imposing some sort of parity conditions to the leading order. So this is the action for a massless scalar field in Hamiltonian form. There is the field, and there is this conjugate momentum. So there is a Hamiltonian kinetic term pi phi dot, pq dot, okay? And then there is the energy density, which is phi dot squared, but pi is equal to phi dot, so it's really the standard kinetic energy. And then there is a spatial gradient of phi squared. So this is the action for scalar field. And now if we say we are going to assume asymptotically that the scalar field goes as 1 over r, now the momentum is related to the time derivative with respect to phi, but with respect time being Minkowskian time. If you compare that with the s derivative, recall that between s and t there is a factor 1 over r. So the pi will, because of that, pi will start 1 over at 1 over r power more than phi, okay, because that comes from s. And so it's natural to assume that pi goes as 1 over r squared, and then some subleading terms, okay? But if you do that, you can easily see that this action is ill-defined for generic configurations. And really, I take seriously the action. I want the action to be finite, on-shell, off-shell, because the action has some physical meaning. And if I want the action to be finite, I have a problem if I say my phase space is given by these variables. Why? Well, you can see that the leading divergence will be, well, the leading term in pi phi dot will be of order 1 over r cubed. So I will have to integrate.
For the same reason, isn't it that phi dot is going to reduce by 1 against the power of r?
No, but even that. No, but this is, so phi dot, it's really phi dot with respect to Minkowskian time, not with respect to hyperbolic time.
Yeah, that's why you should reduce the power by r. By the same, I thought it was exactly the argument.
No, but no. I'm not using equations of motion. I'm saying my phase space is given by that. It's true that phi dot on shell will be reduced because it will be pi, okay? But the action is interesting off shell. So I'm saying I'm considering off shell configurations which are of this type, where phi is an arbitrary function of time and angle, and pi is an arbitrary function of time and angle. I have to define phase space for you. So I'm saying what is pi, what is phi, this is what I consider. Of course, on shell maybe something will happen, but off shell I have to be able to pass integrate my exponential of the action over off shell configuration. So I will not assume that phi bar is such that the equations of motion are satisfied. Okay? Then phi dot generically will be this off-shell function divided by r. Okay? The time derivative, okay, divided by r. So what is it? It will be 1 over r cubed, which I have to integrate over space. And space, if I go to polar coordinate, will give me r squared dr, and then integration over the sphere. So I have r squared dr, 1 over r cubed, so I have dr over r, so I have a logarithmic divergence. So my action for this phase space defined this way is logarithmically divergent. And one way to kill the logarithmic, but of course it will be the logarithmic divergence when I integrate over r multiplied by an integration over the sphere of these coefficients, this phi dot bar dot times pi bar. And if I assume that phi bar and pi bar have opposite parity properties, the product will be odd, and when I integrate over the sphere I get 0. Okay, so that's one way to kill the divergence. And so the standard way to kill the divergence is to say I will take phi bar even and pi bar odd, and that corresponds to removing the Q branch. And then we see that removing the Q branch, which removes this unwanted log r over r in the expansion, has also the additional benefit of making the action finite, or the kinetic term in the action finite. Well, you can also you can show that the generators are then finite, boost, etc. But there is another way to make this odd, which is to take phi bar odd and pi bar even, which is to keep the Q branch and drop the P branch. I think from the point of view of the Hamiltonian formalism, at least I have not been hit by this choice. So I think it's equally good. It gives a bad description of null infinity, but I would say this is the problem of the null infinity people. Sorry? But there is an alternative. This alternative has not been much explored, but I think it's interesting, and we will see that, and actually there are similar alternative possibilities in gravity.
So if you do the electromagnetic wave coming from an internal antenna or something like that, don't you get an answer to this? Meaning, like, don't you get leading behavior in 1 over r that you...
I think there is still some freedom because there is a decoupling between the angular component and the radial component. So,
if you fix the internal antenna to exist, you have a source for the electromagnetic field. You can compute what it is. It's not a choice. It's what it is, right?
Yes, but I don't think that all the components are non-vanishing, and so there are some vanishing components, the parity of which you can still decide. I don't think it will fix completely the whole problem. So indeed, one way to decide would be to consider more solutions that you want to incorporate in the phase space. I think it's natural to take even and odd, but I'm not completely convinced that the other possibility is not consistent all the way. Okay, but to summarize, we see that imposing parity conditions on the leading orders, and including, and if you consider in particular keeping the P branch, it has the good properties of giving you an action which is finite and eliminating the leading log divergence in the expansion near null infinity. And these a priori seem to be two completely independent requirements, but they meet. I will argue that they are not completely independent in the next lecture, because if you look at the generator of the boosts, you will find that they diverge if you don't impose parity conditions. And really, when we go to null infinity, we are making boosts of infinite velocities. Okay, but in any case, this is another story. So let me just conclude now. So as I said, we can integrate explicitly the initial conditions for a Klein-Gordon field, which has long range, so it decays slowly at infinity, 1 over r squared, etc. You get an expression at null infinity, and generically, for generic initial conditions, you will generate such logarithmic terms unless you impose parity conditions on the leading order. As we will show in the next lecture, the procedure can be repeated for electromagnetism, and in 2 weeks for gravity. And in that case, we will also be able to derive matching conditions, which will take the standard form if we eliminate the Q branch. There will also be a Q branch and a P branch. If we eliminate the Q branch for the leading part of the electromagnetic field and the gravitational field. And so with this, I will close, and thank you for your attention.